My name is Matteo, and yeah, I've prepared a few lectures on enhanced sampling. And my first, my idea for today is to try and collect questions and try to answer them live on the material that was made available last week. And then perhaps if we have time, also cover some additional ideas that relate to the material that we've covered, and also relate to my research. So I don't know, perhaps I can see around 10 people connected. So perhaps it would be good to have I don't know, a short round of questions if you have any, really. To get started, maybe it would be cool if I think it's possible, given the number, if everyone says really quickly, either using the chat or the mic, what they're interested in, and if they had a look at the material, how they may be interested in using the material in their own research. I think that would be an interesting way to start. Feel free to unmute yourself or to use the chat. Anyone? Yeah, sorry, Ahmed. I was whether first of all, I wanted to start with a few answering questions, whether you have any on the material, and I wanted to break the ice a bit by perhaps mentioning quickly what you're doing what are you doing in your research, and perhaps if you thought about it, how can you potentially use these ideas on enhanced sampling in your research?
Okay, can you hear me? I can start. Yeah, so I'm a PhD student.
Yes, I can.
Yeah, I'm a student at Imperial College, and I'm doing my research on thermodynamic models for peptides. I can't think of anything right now in terms of a relationship between the material and the research, but if something comes up, I'll let you know.
Okay.
Thank you.
Anyone wants to weigh in? Okay, perhaps then I'll start covering some ideas, and if you have any question, please stop me at any time, both on the material that I'm covering now and on the stuff that is available online and was recorded last week. So let me see if I manage to share my screen. I have to. I have to quickly, I'm sorry, I have to give some permissions to share the screen. I have to quickly get in and out of the session. I'll rejoin in a second.
Okay.
Okay, I should be back, and I should be able to share my screen now.
Great, we can see and hear you.
Okay, so that's my. Can you see my screen now?
Yeah.
Yes.
It's not what we need to see though.
Fantastic, fantastic, thank you. Yes, but it should be. Okay. Okay. Do you see a presentation now?
Yeah.
Fantastic. Thank you. So basically, I wanted to use this. I mean, in the material that was covered online, I actually tried to bring together ideas that allow you to bridge the gap between sampling the trajectory generated from a molecular dynamics trajectory, from a molecular dynamics simulation of an atomistic system, and computing the thermodynamics associated to transformations that are observed in that trajectory. And if you recall, some key ideas in that type of relationship were related to basically building probability densities as a function of reaction coordinates or collective variables for the system, and then introducing a bias potential aimed at facilitating the sampling of those probability densities, and then essentially being able to treat the bias potential introduced correctly in order to account for its introduction. So basically, in order to recover equilibrium properties given of the real physical system. So I'll go back a second because I want to start from this slide that actually showed the two stages that are involved in umbrella sampling. Umbrella sampling is this technique that's based essentially on running independent bias simulations in which in each of them a static bias, so a bias only dependent on the position in collective variable space indicated with S, is introduced. And then in each of these independent simulations, one basically the perturbation theory expression that we've discussed in the material online is applied in order to obtain an unbiased free energy estimate. And then all those unbiased free energy estimates that are defined locally in each one of the windows that are represented in this slide as these disconnected locally converged branches or pieces of free energy surface are then put together to obtain a collective global free energy profile. So
can I just
see if I manage to move away? Yeah.
Sorry.
Yeah.
Your screen, it's sort of showing most of the presentation, but it's cutting off I think that's global, is it? Yeah, it's cutting off the sort of start and the end of it. So you might want to do full screen.
Let me see if because my
it's partially showing what's behind it.
Is it better now? Is it better now?
It's kind of, I don't know, it's sort of written calculations that you've got behind it.
Oh.
So I don't know if it's got, I don't know what it's doing. It's not dreadful. I think everyone can cope.
Yeah, okay, let me see if it's better like this. Is it better?
It's not shared now.
Let me unshare. Oops. Okay. Now should be better. Let me move away this. For some reason, when I share the screen, my mouse disappears, and I have a bit of a. Okay. Is it better now? This should show only the slide full screen.
I think this is better, yeah.
Fantastic.
Okay, go with that then.
So
yeah, that's perfect. Right, I'm going to leave then. I'll leave you to it. See you.
Fantastic. Thank you for the feedback, Karen. Bye. Thank you. So I mentioned that last time we looked into how basically, performing these bunch of independently biased simulations and then taking care of the bias in each of them in order to obtain the equilibrium free energy associated to the system in each of the independent simulations. And that is the first step that you see on the left. And then ideally one needs to align all these probability densities of energy surfaces and in order to obtain a global profile. And this process was obtained for example, doing umbrella sampling by performing the unbiasing in each window, and then by using the WAM algorithm, the weighted histogram analysis method algorithm, to compute the constants that allow to offset each individual profile and obtain a continuous global profile of free energy. So today I'd like to introduce ideas that basically allow you to get around this problem and that are related to basically getting around this problem by not computing the absolute value of the free energy, but by computing the mean force in each window and then integrating to obtain a free energy profile. And the application that I'd like to mention is based on a method published in the early 2000s by Kasten and Thiel that's called umbrella integration. But I'd like to discuss it in the context of metadynamics, which relates to some of the work I've been doing with my group. And I want to use this example just to show that these ideas related to thermodynamic integration applied to bias simulations can be applied also when the bias is time dependent and follows, for example, an update schedule that is the one implemented in metadynamics. So this is so basically, if we start looking at this problem, the free energy surface function of a collective variable S in a bias system can be computed as a function of the probability density of the bias probability density PB of S and the bias potential V of S. And the expression we have here is the same expression we looked at in the notes and during the recorded lectures. And it's made up of three terms. The first term relates to the bias probability density. The second term is the bias, and both these terms are function of the collective variable S. So they are dependent on the position in S. And then there is this third term, which is an ensemble average in the unbiased system of the bias potential. And if you recall the perturbation theory expression, this number, this component is associated to the free energy difference between the unperturbed and the perturbed ensemble that are generated introducing this bias potential V of S. An important point is that this V of S is not function of S, it's constant. But if we want to obtain a global free energy profile, for example, in umbrella sampling, we need to estimate it for every window independently. So this term plays a big role in umbrella sampling. It plays an important role also in metadynamics, because that term in metadynamics becomes a function of time, and it can become important in order to being able to reweigh in metadynamic simulations. So the alternative way that I would like to discuss in order to essentially do the same thing without bothering about this constant term is resorting to essentially computing the mean force. And basically, this starts from the consideration that this ensemble average of the bias potential function of S is constant in S. So if we take the derivative, and basically the derivative of this free energy surface is the mean force in collective variable space, where collective variable is indicated by the variable S, which is, as mentioned in the recorded contributions, it's a proxy for a reaction coordinate. Basically, if we do this, we get rid of the third term of the constant in S, and we can obtain a continuous profile in principle without bothering computing this variable S. Now, this idea is borrowed by this umbrella integration paper from 2005, where this is done for umbrella sampling, where basically the constants for alignment are not computed, And by assuming that the bias potential is always harmonic, the expression for the mean force in S can be computed analytically. And in that paper, the other assumption that is introduced is also that the bias probability density in S is Gaussian and centered around the center of the umbrella perturbation. Now this works. This works in this example, but it works also when the bias potential is updated in time with metadynamics. And so what I'm going to discuss next is how we can actually take into account this approach. So how we can actually adopt this approach that focuses on computing the mean force rather than the free energy in S to get around this problem of realignment. And to do that, I would like to recall the metadynamics algorithm that I've introduced in the last of the 3 videos uploaded. So the metadynamics algorithm, if you recall, introduces a bias potential that changes in time, and it changes in time by summing Gaussian kernels, essentially. Gaussian kernels that are centered around the position in collective variable space where the system is at the time of the update, and that have a certain height and a certain width. Now, the point is, it is convenient to write the bias potential as a quantity that changes in time continuously, as it's indicated in the integral that we have introduced in the recorded lectures, and that you can also find in the additional material that's available through the TYC site. There is a review on metadynamics that discusses the expression for the bias potential and uses an integral. However, from an algorithmic point of view, the bias potential is updated in discrete steps. So the system, essentially, imagine you start with a completely unperturbed system. Your potential energy will be the physical potential energy of the system without any bias. And then at a certain time t, you add a Gaussian. So that is a perturbation. That is the first perturbation you add. And then you will evolve your system under the effect of that perturbation for a number of steps that corresponds to a time interval tau. Now, that time interval tau separates one update from the next update. At the time t plus tau, you will perturb the system again with a new Gaussian, and the total bias potential will be updated to the sum of 2 Gaussians. Okay. The point is that between two consecutive updates, the system is actually evolving under a bias potential that only depends on position and does not depend on time. So in between each one of the updates, we can actually apply the same idea that was applied in umbrella integration. And we can actually obtain information on the free energy of the system. I think I received. Are you? Did anyone write a comment or? Let's see if I can see it here. No. I'll try to get around this and answer questions later, because I cannot access the messages. So the idea is basically we can compute the mean force instead of the free energy in S between 2 consecutive updates, and then we know an expression that we can use to compute this mean force, because we can apply essentially the same expression that was used in umbrella integration, and that comes from taking the derivative of the free energy. And this expression will have 2 components. One component that is the perturbing force in S, and has to do, basically depends on the bias probability density PB of T, where the subscript T now indicates estimates of this bias probability density that are sampled in a certain iteration between T and T plus tau. So basically, those contributions are accumulated. Sorry, those distributions are computed for every iteration independently. And then the bias force, which is the derivative of the total bias at time t. Okay. Is there any questions so far? So here I'm using, I'm referring a lot to the material that was covered in the second video. So how to take into account the bias potential in the calculation of a free energy surface. And then some of the ideas that are also mentioned in the third video where I discussed umbrella sampling and metadynamics. So the idea now is in metadynamics, you don't have just a single iteration. So basically these expressions are allow us to get the unperturbed mean force in S in one iteration. But then, in metadynamics, we are updating the bias potential a number of times. I mean, thousands or more times in a single simulation. So how do we account for the total bias potential? Well, we use basically we introduce a weighted average of the mean force in S, and we indicate with subscript T the weighted average of the mean force in S at iteration T. So that is given as a sum over all the, that is computed as a sum over all the iterations of the mean force computed in that iteration, and the weights that appear in this sum are also position dependent, and they are computed as the bias probability density in S. Essentially, I'm saying that in every point in S, I will weigh the estimate of the mean force that comes from a certain iteration from the bias probability density sampled in that iteration. And basically, now we have, if we use this weighted average to compute the global mean force in S at time t, we have an analytical expression for that expression, for that mean force in S at iteration t. So the argument of this mean, so the f in the t at time t prime that appears in the first equation up on the left, can be computed from the fact that we know what the bias potential functional form is, and we can take the derivative. It's a sum of Gaussians, and we can do that. And then we can introduce a kernel density approximation. We can introduce a kernel density approximation of the bias potential. Sorry, of the bias probability density, PB. This basically allows us to compute that derivative analytically, and we come up with an ugly expression for the weighted average of the mean force in S at iteration t that can be determined from the simulation, and it's basically can be computed on the fly from our simulation. So just to illustrate how this works, at time t0, we add a Gaussian. So basically, we update the perturbative force that comes from the fact that we are adding a perturbation to the bias potential. And then between t0 and t1, we sample the bias probability density, and we accumulate the contribution to the force that comes from, basically, we compute the total force under the effect of that perturbation. Then at the end of this iteration, we compute the unperturbed mean force, so the argument of the averaged global mean force, and then we update the estimate of that appears in that weighted average. And I just want to show you. Let me try and look at the messages, because. not sure I can see the messages here.
I can tell you.
Fantastic, that would be great.
Yeah, but there aren't any messages at the moment.
Ah, okay, okay. Because I was keeping, I kept hearing some notifications, so I was thinking about that. Thank you for letting me know. So if you have any question, please stop me.
Sure.
So far the idea is okay. It's useful to compute the mean force instead of computing the free energy directly, because we don't need to align any independently sampled, independently biased simulation. And this has been shown for umbrella sampling in this paper from 2005. And what we've been doing is actually trying to adapt this idea and demonstrate that it works also for a time-dependent biasing method, such as metadynamics, when we actually can assume that the bias is updated in discrete steps. So basically, is updated, is updated in discrete steps. So we have a period of time between t and t plus tau where the system evolves under the effect of a bias that is static. So this movie now shows a bit how the simulation works and how the method works for a simple double well potential. And I want you to have a look at, I mean, there are three panels. In the panel at your left, you have the free energy surface that is reconstructed on the fly as the simulation progresses. In the central panel, you have the mean force that is estimated as a weighted average of the mean force that comes from every independent simulation. Sorry, and every independent iteration of the biasing of the bias simulation. So in this case, from every iteration of the metadynamic simulation. And in the right panel is the error, which is indicated as the average in S of the absolute error. So the difference between the reconstructed free energy and the exact free energy in S. And so basically, here you're looking at, in the leftmost panel, you're looking at, in red, the reconstruction of the free energy, in blue, the analytical expression of the free energy surface, that is a reference, and then in green, you see the weights. So these weights are position dependent, and they are reset every time you add a new Gaussian. So they're accumulated from the sampling that comes from the interval tau between two successive iterations of the bias potential, update. In this leftmost plot and in the rightmost one, there is also a traditional estimate of the free energy that comes from integrating the bias potential from a metadynamic simulation. So that gray line represents the standard way of computing a free energy surface from a metadynamic simulation. So if I let this go, you should be able to see a movie where the system moves around between the two metastable states, and it does move around because the bias potential is kicking it outside. It's basically enhancing the probability of observing a transition across the high free energy barrier that separates the two metastable states. And then basically in red, you see that the estimate of the free energy that comes from the integration of the bias is actually converging faster than the same estimate coming from the normal integration of the bias potential that is typically performed in a metadynamic simulation. And one of the reasons why this convergence is faster is the fact that the expression for the free energy that we have introduced in the third video, and that relates basically only to the bias potential in the case of a metadynamic simulation, is only valid at basically for long times. So for times that reaches, so for the sampling that reaches the limit distribution for that particular method. So in the case of well-tempered metadynamics, for the system reaching the limiting distribution for well-tempered metadynamics, and for standard metadynamics for the system reaching a diffusive regime between the minima. In this case, instead, the expression that we're using is always valid as long as we can estimate the forces that are coming from the basically, as long as we can estimate the first of the two terms, these term that depends on the logarithm of the bias probability density at time t. So the point that I wanted to make with discussing this application of an integration approach is not that I mean, basically this is an alternative way of computing a free energy surface from a metadynamic simulation. The point that I find interesting is that as long as you can converge these bias probability densities between iterations, you can actually converge a free energy profile, and the convergence is faster than the normal estimator. But the most important advantage of this technique is that in principle, the weighted sum that we are using and that is indicated up here, in order to estimate the global mean force coming from all iterations at time t in S, well, this expression can be extended to independent simulations, and those independent simulations do not necessarily need to know of each other's existence. Essentially, we can take a property that is typical of umbrella sampling, where you can initialize independent simulations that do not exchange any information with other simulations in order to improve the convergence, the local convergence of the free energy surface. Well, you can do that using this mean force integration idea. You can do it also for a metadynamic simulation. So also for a simulation that is typically instead a serial one, because you know your molecular dynamic simulation needs to generate a continuous trajectory that is then used to estimate your free energy surface from using traditional ideas to compute a free energy surface from metadynamics. So I want to show you an example of this, just to give you a grasp of why that might be useful. And this example is related to an application of metadynamics to sample the conformational free energy associated to the conformational free energy associated to transitions between different conformers of an organic molecule, in this case ibuprofen, in its crystal bulk. And I have allow me to jump here. So ibuprofen is this molecule, and the two collective variables that we are using to represent this free energy are these two torsional angles. A torsional angle that describes the relative position of substituents on this aromatic ring. So basically, it describes the relative position of the carboxyl group and of this alkylic group. And the second torsional angle that describes the relative, basically describes the rotation of the two methyl groups around this bond. So the configurational space that is sampled is characterized by six conformers that have a characteristic relative orientation between groups. And the point is that in order to converge a free energy surface using the integral of the bias potential, one needs to run simulations that are that sample this configuration space with a biased strategy for hundreds of nanoseconds. So in other words, if you run your unbiased simulation, the entire simulation of this for this system is stuck in conformer C1, so in the lower left corner of this conformational free energy surface. And then if you bias instead, you can explore other conformers that are adopted by this molecule in the bulk of its crystal phase, and you're able actually to identify C2, C3, and others, C4, C5, and C6 that are located elsewhere in this free energy surface. However, in order to converge a free energy estimate, you need to run for more than 100 nanoseconds. So our idea was, can we use this method to actually run instead of running independent, essentially instead of running a single metadynamic simulation that is extremely long in time, we can break it up and run independent simulations, and then patch them all together in order to obtain a global estimate of the free energy surface using this mean force integration idea. So this is what we did, and in this first reconstruction of the free energy surface, I'm showing a first batch of simulation that are initialized in any one of these 6 free energy minima that are indicated with labels C1 to C6 in the plot on the left, and basically we've pushed together the estimates of the free energy for these simulations and obtained these estimate of the free energy surface. I have to say an estimate that is only accurate for C1 to C3 transitions, because we can actually obtain reversible transitions in this regime. In other words, we can get estimates of the mean force going in both directions between all of the minima between these states. Then we introduced a few other simulations that actually sample specific transitions that were not sampled reversibly in the previous batch. So basically, we introduce simulations that start from C1 and reach any one of the 3 states, C4, C5, or C6. And then we do the same for simulations initialized in C4, C6, C5, and C6, basically. And this allows actually to reconstruct the entire free energy profile, and to a very good accuracy, essentially. This in the center top, this panel in the center top represents a block average of the free energy estimates coming from this independent set of simulations. So I want to point out something here, which is the last column of the table on the table on the right, sorry, which is the characteristic length, the average length in terms of simulation time for every one of these transitions of these simulations. So now basically we have transformed a problem that required to run a single trajectory for more than 100 nanoseconds into a problem that we can break up in independent simulations. And the longest independent simulations that we need to perform in order to converge this type of free energy surface are 1 order of magnitude shorter in time, and also can be parallelized trivially, in the sense that we can run independent simulations at the same time in order to reconstruct essentially the same information. The information that is reconstructed is really compatible between the 2 methods. And in this slide here, we are actually showing with a colored surface, the free energy reconstructed from mean force integration. Instead, the isocontour that are highlighted in dashed blue are the isocontours of a free energy surface computed with the integral of the bias from a long metadynamic simulation. So the idea is, as long as we can get transitions from minima, we can converge this free energy surface. It's important that we have transitions between minima in all directions. However, and this is the advantage compared to the normal metadynamics approach, we do not need to have transitions in both directions in the same trajectory. We can have independent trajectories sampling transitions in different directions, and then we can patch them all together with this approach and obtain a global free energy surface. Okay, so I'd like to stop it here and ask whether there is any question. Do you have any comment or question on this stuff? Is there anything from the material discussed online that you want to clarify or ask questions about? Okay, so would you be interested in I can talk about two things. One thing is using bias dynamics to obtain information on the dynamics of a system. So far, I've only discussed about being able to compute free energy surfaces from sampling of a configuration space projected in some proxy of the reaction or the reaction coordinate of a reaction coordinate. An alternative thing that one may be interested in doing is computing rates. So would you be interested in me touching on that, or would you be more interested in me showing some applications or of bias sampling?
Maybe application.
Okay. Okay, applications. Okay, so I have a couple of applications that come from my research and that are related to phase transitions. And in this context, I think let me see where I can jump. Yeah, I think this is the application I wanted to mention. So what I want to highlight. Oops. Get rid of this. I finally figured out how to. Nope. I'm sorry. I keep losing my mouse when I share the screen, and this is really awkward. Okay. So so this is an application of some of these ideas to sample the configuration space of a crystalline material. So in particular, in this example, we are looking at packing polymorphism of CO2 under pressure. And CO2 is a relatively simple molecular compound, but it has a very convoluted phase diagram, especially at high pressures. This phase diagram is characterized by a region that is non-molecular, but then that also by several polymorphs that coexist in when CO2 is in its molecular form. And the most common arrangement of CO2 in the crystalline phase is this phase 1, but there are several other polymorphs available. And the transition that I'm interested in discussing here is the transition between phase 1 and phase 3. So basically using bias sampling in order to obtain information on the thermodynamics of this transition and of the dynamics and of the mechanism of the process. And so basically in order to do that, the first thing one needs to do is to find a proxy for a reaction coordinate. So some way of representing in a low dimensional fashion the reaction coordinate that connects phase 1 to phase 3. And a starting point for identifying basically a low dimensional representation of these reaction coordinate is by looking at a concise way of representing the crystalline structure of CO2. And in particular, here we look into being able to represent the level of order and density of CO2 in the condensed phase. And in order to do that, we look at the characteristic angle between neighboring molecules. And we recognize that that is very different when you go from a random packing to an ordered packing. And in particular, this angle is also interesting because it's characteristic of these two different phases. So it's characteristic. It assumes characteristic values from phase 1 and phase 3 respectively. So we use this idea to implement collective variables that basically are maximized when the angle between neighbors is in a certain range, and that therefore reach like a maximum value for the system being in phase 1 or in phase 3. So in particular, we use this formulation on the left for a collective variable, where we have essentially that the global collective variable indicated with lambda. Sorry for the thing here. The collective variable indicated with lambda is an average over all the atoms over all the molecules and in the system of a molecular order parameter gamma I, and that order parameter gamma I is given as an average of a function that depends on the relative orientation. So this function that depends on the relative orientation is indicated as a sum of Gaussian kernels, and the Gaussian kernels are maximized for a value of the angle that is characteristic for a certain phase. So in particular, in this case, we have that lambda 1 will have characteristic values that are around 80 degrees, and instead the phase 3 will have a characteristic value for these angles that are close to 0. So these kernels are positioned, these Gaussian kernels are positioned in such a way that we basically minimize the overlap of the overlap between configurations projected in the space of collective variables that belong to different phases. In fact, if we project where the different configurations for CO2 are represented in this space of lambda 1 and lambda 3, where 1 and 3 refer to the two phases, actually we can see that they don't overlap, and therefore the variables that we're using are actually working in distinguishing between the two sets of configurations. Now, this process is necessary because we want to be able to introduce a bias potential and represent our configurations in a low dimensional space. So this space of lambda 1 and lambda 3 is analogous, basically plays the role of the variable S that we have discussed in all the videos and also in the earlier example. And so once we have this representation, one can ask, why do you need two variables? For example, lambda 3 already does a good job in separating out configurations. So if you imagine to project this in one direction, you may have in one dimension, you may have that phase 3 and phase 1 are well separated in either lambda 1 and lambda 3. However, if we imagine configurations that are completely disordered and therefore have a low value of both lambda 1 and lambda 3, actually they would be degenerate to one of these two phases if we use the single monodimensional collective variable space. So we use this two-dimensional collective variable space in order to avoid the overlap between one of the two phases and a disordered phase. So now, basically, what I want to show you is that what happens when you introduce a bias potential with a metadynamics algorithm for this transition. So what's happening here is that we start from one configuration, and then by introducing a bias potential in metadynamics, we are able to sample transitions between the two different phases. So the system in this trajectory is going back and forth between form 1 and form 3, and it's exploring different configurations that are characterized by different distributions of the relative orientations between molecules. Okay, these are the other ingredient, or the other aspect that was discussed for this type of free energy calculations is essentially being able to compute a free energy surface in the space of the collective variables that we have discussed, that we've introduced, sorry, in this case. So here I'm showing a typical free energy surface that is reconstructed in the space, in the collective variable space defined by lambda 1 and lambda 3. And this is reconstructed for a particular temperature and pressure. So it's a 350 Kelvin, 5 gigapascal. And in these conditions, we have more than two local minima, actually. So we can see that we have one local minimum for high values of lambda 1 that corresponds to phase 1. Then we have one local minimum for high values of lambda 3 that corresponds to phase 3. And then there is a region that connects the two of them. There is a low energy pathway between the two of them that goes through basically this band that bends in this space shaped like an L. However, there are also local minima that are outside this path that connects the two states, phase 1 and phase 3. And this local minima actually corresponds to defected realization of some of the configurations that are sampled. In particular, they correspond to defected configurations that correspond to phase 1. So in this movie here, I'm looking at the formation of some packing defects that are sampled during, you can see, for example, at this point, oops. At this point, the formation of a packing defect in the crystalline phase of, here it is, of a crystalline phase of CO2. So it's phase 1, but contains defects. And these configurations are actually identified found independently during the sampling of the configuration space. And they're found consistently at different temperatures. So one can, for example, study what's the importance of defects, of these defects emerging in the bulk of the crystalline phase as a function of temperature. We can, by looking at the dependence of temperature of the free energy surface, one can also have an idea of the phase diagram of these of the model that is used to generate these free energy surfaces. So in particular here, we can basically repeat this simulation in different conditions. And if we are below the equilibrium, the liquid-solid equilibrium curve, we can actually observe that the system does not have anymore these two states. It's not characterized anymore by these two metastable states that correspond to crystalline phase 1 and 3, but it's characterized by a single minimum that is a correspondent of a liquid phase. Then if we move up in pressure, we actually see that the two states start to emerge. And if we increase pressure, we see that the difference, basically the difference in free energy between the two states changes. So one can actually also change temperature and see something similar. So if we increase temperature up to a point where we overtake the melting temperature at a given pressure for the system, we see that the two states that correspond to phase 1 and phase 3 disappear, and we have a single minimum for the system that corresponds to a disordered liquid phase. So one can actually look at the difference in free energy between the states, and what we observed here that was kind of interesting is that basically the defects that are included in essentially in computing the weight of configuration 1 of polymorph 1 in the blue curve start to play an important role at high temperatures. So at low temperatures, these states exist. They're sampled, they're local minimum of the free energy surface for this model, but statistically they don't weigh much. But as temperature increases, the weight of defects increases. So essentially the probability of observing defects in phase 1 should increase with temperature. And then the other important thing that, you know, when I've been discussing collective variables, I always said these collective variables should approximate a reaction coordinate. And one of the aspects of this approximation is the fact that a real reaction coordinate should be able to distinguish between the two states, so the two reactant and product states, in this case phase 1 and phase 3, but should also be able to characterize correctly the transition states in the system. And this transition state associated to the transition between the two basins, the two configurations of your system. And if we only use the collective variable space characterized by lambda 1 and lambda 3, we see that the apparent transition state in this collective variable space that corresponds to a saddle point along the path that connects the local minima, it's not really behaving like a transition state should behave. And this has been analyzed by performing a commuter analysis and an histogram test. And this histogram for a real transition state should show a nice a nice bell-shaped curve and in the middle, around 0.5. And you can see that this is not the case for the space of collective variable that involves only lambda1 and lambda3. However, if we introduce the anisotropy of the simulation box, we can actually reconstruct a three-dimensional free energy surface by reweighting, introducing this third parameter. And in this case, the bottleneck along the bottleneck in free energy along these path that connects phase 1 and phase 3 actually does behave like a transition state. So we can look at configurations that correspond to this transition state, and we realize that these configurations actually have an independent, have a distribution of relative orientations that is neither phase 1 or phase 3, and basically there is a collective reorganization of the system that undergoes and that corresponds to the transition state for this particular system. So I wanted to show this example because this example kind of puts together several ideas that we have covered in this short part of the course on enhanced sampling. And the key ideas are the following one. The first one is that we choose to represent the system in a low dimensional space that we indicated with S in the discussion in the previous discussions, and that low dimensional coordinate space has to be able to distinguish relevant states for the system. So in this case, it has to be able to distinguish reactants and products. The second point is that by adding a bias potential, one can actually effectively sample transitions that would not happen in an unbiased simulation. And the example here is given by this movie that I showed about the transition from one state to the other of CO2. And then once you introduce that bias, once you introduce that bias potential, one can actually come back and compute the free energy surface associated to this type of configuration of space. And on top of that, basically, if you're able to do that, basically you can also get information on the free energy surface, on the phase diagram, on the presence of defects, and you can also further analyze the collective variable space to have information on the mechanism. Okay, so this is it, and I think we're also up with time, but I would like to encourage you to ask questions if you have any now, or if you want and you're interested, you can email me questions, and I'll be happy to answer asynchronously, as they say in these times. So yeah, any comment or question? Nothing? Okay, is there anything else you want to discuss, to ask, or to mention overall? Okay, thank you, Victor, for your comment. If anything pops up that you may be interested in discussing on the application of this for your particular problems, or anything that doesn't make sense in what I've discussed either today or in the recorded lectures, do not hesitate to feedback and to email. Okay. So yeah, if there's nothing else, I would close the session. And thanks for attending. And yeah, please let me know if I can help any further with anything related to this topic. Okay, good. Okay, so I'm gonna close it. Have a great day, and bye everyone.